Welcome to this video lecture on testing a mean or proportion. We begin with testing a mean, and we begin with testing a mean when the standard deviation of the population, sigma, is known. So we have a situation where there's a certain hypothesized value for the population mean mu. This is the value that the population mean is believed to be or supposed to be, and we want to take a sample from that population to see if that is the case. So we call this a one-sample Z test because it uses a Z-score from a normal distribution. And we know that sample means are normally distributed. So the test statistic Z is calculated as x bar minus mu in the numerator of the fraction. Now that's perfectly sensible. If you never studied statistics, that is what you would do. There is some hypothesized mean for the population mu. You want to see if that's the case. What would you do? You would sample a few items from the population and you would calculate the sample mean x bar, and then you would look at the difference between x bar and mu. Is there a big difference between what it's supposed to be, mu, and what it seems to be, x bar? So x bar minus mu shows the difference between the evidence and the theory, between our observations and our expectations. And that quantity, x bar minus mu, that difference is divided by sigma over root n. And that is the standard error of the sample mean. In other words, that is how big we would expect that difference to be. So we're really asking the question in this statistic, is the difference much bigger than expected? So we calculate Z and then we see if it's in the rejection region by comparing it with tables of the normal distribution. So we use this when we're testing a population mean and when the standard deviation of the population sigma is known. So here's an example that uses that formula. We have bags of peanuts that are claimed to weigh not less than 25 grams on average. So there we have a hypothesized population mean mu, which is 25. We know in this case that the standard deviation of the bag weights, sigma, is 3 grams. And we want to test that claim, and so we take a random sample of bag weights which are displayed here. So we will use that sample to calculate the sample mean. We won't calculate the sample standard deviation because we have something better. We know the population standard deviation. So from the sample we will take the sample size, which is 6, and the sample mean, which is x bar, and substitute those values into our Z formula. So we lay out the hypothesis test by stating the null hypothesis, mu equals 25. We state the alternative hypothesis, mu is less than 25. Notice that the claim is that the bag weights are not less than 25 grams on average. So only a departure on the less than side would lead to rejection. We don't mind if the mean is bigger than 25. That's not of interest to us. So this is a one-sided test or a one-tailed test. X bar equals 22, that's the value we calculated from the sample. N equals 6. We substitute those values into Z and we get minus 2.449. So the sample mean is 2.449 times lower than the mean, than what we would expect it to be based on the standard error. So the question is that in the lower 5% tail? The critical value from the tables, which I'll show you in just a moment, is minus 1.645. And so our calculated value of Z, minus 2.449, is more extreme than this. So it is in the lower 5% tail. The calculated value of the test statistic falls into the rejection region. So the p-value is less than 5%. We reject the null hypothesis in this case. The null hypothesis that mu equals 25 is rejected in favor of the alternative. Mu is less than 25 grams. Here's where we found that value in the tables. These are the tables of the t-distribution, but the final row of the t-distribution on this second page of tables with the entry infinity on the leftmost column, that t infinity is z, we look across through that final row of the table and we look underneath 0.05, which is the second column in the table proper. 0.05 because there's 5% in a single tail, and the value there is 1.645. But since we know that we're dealing with the left tail, we know that it's minus 1.645. So that is how we identified the critical value, so that we could identify that our calculated z-score was in the rejection region. This next example takes the same problem and shows how we would solve this problem if the standard deviation of the population was unknown. And of course the formula looks very similar. T is x bar minus mu, this time divided by s over root n. S is the standard deviation estimate that arises from the sample. And of course when we use s instead of sigma, we use t instead of z. The t distribution is based on the estimated standard deviation. So we use this test for the same purpose, to test if mu equals some value, and we use this test when the standard deviation is unknown. So we have the same problem and the same data, but this time we don't know the population standard deviation. So we will use the sample not only to provide values for n and x bar, the sample size and the sample mean, but also to provide a value for s, the standard deviation. And here we have the hypothesis test laid out again. The null hypothesis stating that mu equals 25, the alternative stating that mu is less than 25, x bar is 22 and s is 2.28, the standard deviation calculated from the sample data. The sample size n is 6, so the degrees of freedom is n minus 1, which is 5. We substitute the sample statistics into the formula and we get a value for t of minus 3.22. We just leave that value there and then we go to the tables to find what is the critical value. So this time we take the t value from the tables, which I'll show you in just a moment, and it's minus 2.015. So we're looking at the t tables with 5 degrees of freedom and in the 5% column. Again, the calculated value of t is more extreme than the critical value of t, so the p-value is less than 5%. The calculated value of the test statistic did fall into the rejection region. We reject the null hypothesis. So again, in this case, we can say the mean is not 25. We reject that in favour of the alternative. The mean is less than 25. It just remains now for me to show you where we got that value in the t-tables. Notice again, the degrees of freedom is 5, and we want 5% in a single tail. So here are the t-tables. The degrees of freedom down the leftmost column is 5, so we go to row 5, and we come across through the table underneath the 0.05, which is 5%. And there we read 2.015. And we use our knowledge of the problem to recognise that we need to deal with the minus 2.015 because we're dealing with the left tail. So that's how we test a sample mean, or rather that's how we use a sample mean to test a hypothesis about a population mean. So if you're ready, we will move on to testing a population proportion. So when we test a proportion, we call this a one sample p test, p for proportion, even though the test statistic is actually called z. And as before, the formula is not a big surprise. The test statistic z is p minus pi. P is the sample proportion and pi is the hypothesized population proportion. So again, the numerator of that fraction is perfectly reasonable. We have a belief or a hunch that the population proportion is given by some number pi, and we take a sample and we calculate the sample proportion and see if there's a big difference. So p minus pi is the difference we observe between the sample and the hypothesized population proportion, and we divide that by the standard error of a sample proportion, which is root pi into 1 minus pi over n. So the null hypothesis we're testing is that pi, the population proportion, equals some value of course between 0 and 1, depending on what the population proportion is believed to be. And the conditions for using this test is that the expected number of yes in the sample, n pi, and the expected number of no in the sample, n times 1 minus pi, should each be at least 5. That is because we are using a normal approximation. And so if those conditions are filled, if the sample is big enough, according to those criteria, then it's big enough for carrying out this test. So in words, those two conditions mean we're expecting at least 5 yes in the sample and we're expecting at least 5 no in the sample. Our example that we're dealing with here is a courier made a commitment that not more than 8% of all deliveries will be late. So there's a statement about the population proportion. Pi equals 0.08 is the claim. Not more than that. So a random sample was taken of 315 deliveries and 30 of these were late. Can it be asserted that the commitment has been violated? Can we reject the null hypothesis or not? So we lay out the problem like this. The null hypothesis states pi equals 0.08. The proportion that are late is 8%. Notice the null hypothesis must always have an equal sign. It never says a less than or greater than. We have to test something definite. We have to test a particular value of the parameter. We deal with the other aspects of that in the alternative hypothesis. H1, the alternative hypothesis says pi is greater than 0.08. The contract will be violated if it's more than 8% that are late in the population. N, the sample size is 315, and P, the sample proportion, is 30 over 315, which is 0.095. Now, someone who's very unskilled in statistics might immediately think that the contract has been violated, but that's not true. Just because an individual sample has 9.5% late deliveries doesn't mean that the population does. If the population proportion is 8%, then when we take some samples, the sample will have more than 8%, and when we take other samples, those other samples will have less than 8%. So we still have the open question, does this prove that the sample couldn't have been taken from a population which has pi equal to 0.08? So we substitute the values and calculate the test statistic, and for Z we get 0.98. We just park that number there, and then we go to the tables and look up the critical value, and I'll show you the tables in a moment. The critical value for Z is 1.645. That's the upper 5%. We have one tail with 5% on the right side of the table, and it's Z, so it'll be in the T infinity, the final row of the T table, as I will show you shortly. So the calculated value 0.98 is not more extreme than 1.645. The calculated value falls into the acceptance region. It's quite reasonable that that value would arise if the population proportion was 8%. So we accept the null hypothesis. These data do not prove that the contract has been violated. Here we have the table showing in the final row, T infinity, which is Z, under the 0.05 we have 1.645. So that's where we obtained our critical value for performing the test. So you can read more about this in the textbook in chapter 5.